Welcome back to the OnTrack Whiteboard Series. My name is Ben Jordan, and today we're talking about RF and Microwave PCB design. This is episode 4 in the series, and I know if you've been following along, I promised in the last video that this time we would talk about a device called directional couplers. I will cover those, but I realized there's probably a more fundamental and useful device that you should probably learn about before we talk about directional couplers. So we'll get to those, but a more fundamental basic way of getting a signal to go into multiple places is a device called a power divider. And the power divider, so this episode is about power dividers. The power divider, in its simplest form, takes a shape something like this. So we have a transmission line segment coming in, and let's just call that Z0 of our main transmission line, and that's typically going to be system impedance of 50 ohms, say. And so what happens, we want to split that signal, and there's many reasons we might want to do that. So for a good example is you have an antenna array, and you need to take one feed line that's 50 ohms as an input to the array, but you need to divide that up in phase to many different antenna patches. So we'll talk about patch antennas down the road when we come to our antennas episode. And so how do you split a signal evenly? Well, if I have a 50 ohm transmission line and I have two other 50 ohm transmission lines, so there's one port, so I have this, let's call the input port, port 1, and the output ports, port 2, and we have another one, port 3. And let's say they're all 50 ohms. They're all Z0 or ZO, port 3. Okay. Now what do? We can't just connect two 50 ohm lines in parallel to this 50 ohm line, because then we'd have 25 ohms effective and we'd get reflections that wouldn't be matched. The system wouldn't be matched. So what we want to do where we divide is have 200 ohm segments, so we can split that off effectively into two 100 ohm lines in parallel at that point. This is just theoretically, say, for all intents and purposes. And then we have a perfectly matched junction here. And so where it's matched, there's not going to be any reflections or anything like that, assuming it's designed properly. And then we have this other issue where we have 100 ohm segments, 100 ohm transmission lines, and now those are no longer matched to our 50 ohm output ports. So what we need is some segments which are a quarter wavelength long. Remember in a previous episode we talked about the quarter wave transformer for impedance matching. So that's exactly what we need here. We need a quarter wave transformer that matches our 50 ohm output port transmission lines to our 100 ohm divided transmission lines. And so if you recall from that previous episode, to work out what's the impedance of our quarter wave matching transformers, we need to, let's call those ZA and ZB. Of course, everything's a mirror image on port 2 and port 3 because we're assuming we're splitting to two equal transmission lines. Okay, so ZA equals ZB, ZB, if you're from Australia, like me, equals square root of 100, that's our incoming line split, times 50, our outgoing. And that happens to work out to be about 70.71. Essentially, it's Z0 times root 2. Is that right? Or divided? Something like that. 70.71 ohms. So then the question is, how long does this 100 ohm segment need to be? Technically, it doesn't need to be any length at all. It can be 0. And the reason is, so let's go for this 100 ohm segment and analyze this a little bit further. The effective input impedance at the beginning of this 100 ohm line segment, so let me just change color real quick here. Zn is, in this particular case where you have a quarter wave, so this is 100 ohm. So we're looking at the impedance that's matched at the beginning of the quarter wave transformer. That's also equal to 100 ohm. Zn at the quarter wave transformer is 100 ohm. And why is that? It's because that is equal to, the special case with a quarter wave transformer is that the input impedance of that looking into this quarter wave transformer, which goes on to a 50 ohm impedance, is the system impedance times the load impedance. Well, it's the quarter wave transformer impedance section times the load impedance plus J ZA 10 propagation constant times the length over ZA plus J, the load or end impedance, the port impedance, tan propagation constant times the length. Now, the interesting thing about these terms here is that when length is exactly a quarter wavelength, this whole thing becomes, what it becomes is the input impedance is equal to the quarter wave transformer impedance squared over the load impedance. In this case, load impedance is actually the impedance of the following on system. So Z, that's actually Z0 and this is ZA. And this all leads to this formula down here that we used before. And so we have this, the equivalent input impedance of 70.71, etc. Well, it's basically, it's 70.71-ish squared over 50 ohms. So what's that? That's 5,000 over 50 gives us 100 ohms. So that's why looking into the quarter wave transformer, it looks like 100 ohms already, just looking right in there. So we don't even need these 100 ohm segments. So to divide equal power without reflections at the frequency of operation for a 50 ohm line, we need our input port to divide into a T-junction where we have two, and let me draw them like they would typically be designed with the chamfered corners. We have two quarter wavelength segments of 70.71 ohms, close to that. We have a 50 ohm line coming in. These two quarter wave segments of 70.71 ohms. From this point here to there, it's a quarter wavelength. And then we have our output sections going back to 50 ohms. And this is a very common device, very easy to make on a circuit board. and it's used most frequently for taking a signal and splitting it. And this is from a perfect simulation of one of these power dividers, showing the reflection, the S11 in dB, so the reflection coefficient, and showing the transmission, S21. So there's a couple of issues. Let me just go to another page here on my digital whiteboard. I'm just going to a new page. Okay. It's a couple of issues. First issue, one, this is all DC coupled. So, and that's not always going to be a problem, but it may be. It's just something to consider. Two, it is a multi-port network that is not isolated. What does that mean? That means if you get signals coming in, let's draw this again real quick, and I'm going to draw it slightly differently this time. Here's a typical power divider. Right, with 100 ohm quarter wave segments here. This is just one way of doing it. They don't have to be cornered like this. It's just how I would do it, because typically I'd want, say, a connection coming in here and connections carrying on out in the same direction. So it's not isolated. So here's the problem. Here's port 2, here's port 3, here's port 1. And presumably we have a source from port 1. The problem is any reflections or signal coming from these ports are not isolated. They will, to a degree, go through the system and interfere with signals coming out of and going into and around the other ports. And so unless you have perfectly matched loads at the output ports, and those are typically going to be antennas, right? But what if this is receiving as well as sending? Well, maybe that's okay. If they're receiving the exact same signals, then they add together and don't reflect and don't cause interference, right? So it may not be a problem. And we do see this basic structure used a lot in antenna arrays. But what if you don't want that? What if you need more isolation? Well, there's a variation of this that was come up with by a very clever guy named Wilkinson. And what he figured out was that you can add a termination resistor to this network, and when this divider is functioning normally, there's no dissipation because you have these perfectly matched loads on the output ports. If you have perfectly matched loads, then there's no reflections in the system anyway, and there's no isolation necessary. So what does this look like? Let's go to another page again. And this is the most common implementation of a power divider that I've seen anyway. It's called a Wilkinson power divider. Okay. The Wilkinson power divider is essentially the same structure. So we come in Z0, that's typically 50 ohm. Then we have a split. But what we want to do is put a resistor typically 100 ohms because we're dealing with a 50 ohm system, and we'll have a differential mode impedance between the 200 ohm output ports, the 250 ohm output ports of 100 ohms, right? And so because that resistor is in a small surface mount package or maybe screen printed on the board, we need a very close gap where that, like the distance here is not far. This may be a 0603 package or something like that, something small, because it's not going to be, in normal operation, it's not going to be dissipating a lot of power. Okay, so what we have to do is take our 70.7 ohm splitting segments and curve them or bend them around either as a curve, like an arc, which is how I would like to do it. So we have to design our divider using circular arcs, the circumference of which, this is still from here all the way around to here, is a quarter wavelength. And so when you're designing this, you want to start with the very center and find the radius of your arcs. They're almost 180 degrees, and they for a quarter wavelength, the length of the arc length, S say, is 2 pi r times the angle on 360, right? So that simplifies because angle is almost 180 degrees anyway. So let's just be rough here and simplify it. Now, of course, there's plenty of calculators and spreadsheet tools, and you can work it out based on the actual size and gap from the resistor footprint. There's going to be another angle. Let's call that one theta, and this angle here, let's call phi. So we'll call that phi. Okay, so this is almost 180 degrees. So just for rough calculations, this is roughly what you're going to end up with. You'll have that didn't come out for some reason. Let me just trace over that, 2 pi r. So this is our length. So that equals a quarter wavelength, right? And because this is 180 on 360, that simplifies and cancels out the 2. So we have half times 2. So that equals pi r in degrees. So from there we can work out r is, of course, wavelength on 4 pi. So that's the rough starting point. Wavelength on 4 pi. Oops. It's a bit unclear, but you get the idea. It's very nearly 180 degrees. So that what we're really going for here, just to make it super clear, is we have a quarter wavelength transformer times 2. These are quarter wavelength, and they don't have to be circular. You could go up and have the chamfered corners and come around, but the actual path length of that transmission line transformer needs to be a quarter wavelength. And between them, on either side of the resistor's pads, we have from here all the way around to here is a half wavelength. Why? So that here we're going to have our output ports, which are 50 ohms. Right? port 2, port 3. Now what happens, an interesting thing happens. If any reflections or unwanted signal comes in one of those output ports, a half wave later it's cancelling out with itself, and the 100 ohm resistor terminates that against its own, that same signal 180 degrees out of phase, because it's a half wavelength apart, and that gets dissipated in the resistor. So it does not go out the other port. So you have output port isolation, and it's isolated also towards the input port, and vice versa. So this structure is the preferred structure for a power divider, and there's many designs. Now this particular one takes the form, let's go to a new page real quick. And then we have our quarter wave transformers, ZA, ZB. We have our terminating RDIF. And there's a lot of really cool online calculators to work out the values of all of these. But typically this is a 50-50 split. So we have 100% of the signal coming in here, or 0 dB. And out here we have the signal down by 3 dB because it's cut in half on both sides. So this is called a 3 dB divider, 3 dB Wilkinson divider. And then we have port 2 and port 3. But there are other forms of this that you'll find. You don't have to have two separate impedance transformers. You could have, possibly, another way of doing this is to put one impedance transformer at the beginning. So you could have your port 1 coming in through Z0. Then you have quarter wave ZA here, and then split that directly into two. I've seen that one as well. And then have your RDIF and then other segments after that. So there's many different iterations of this. They all basically follow the same principles and work really well, and very, very useful circuit to do and easy to do on a PCB. So what would that look like? Let me show you a couple that I designed late last night while preparing to make this video. So here's a simple 2.1 gigahertz Wilkinson. It's not a Wilkinson divider. This is just the basic power divider. And I've done that using components I made for the transmission line segments. So these are pre-designed segments that are specific impedance on the substrate. And so here's the actual result after milling. So I have port 1 here coming in, going to two quarter wave impedance transformers, which are 70.7 ohms. And you'll notice something else about this, which I didn't mention before. We have this tiny little, where the 50 ohm line comes in and splits, I have this tiny little notch taken out. Let's quickly go back to here. Tiny little notch taken out. And that's to prevent the t-junction from causing too much of an impedance anomaly. Generally speaking, when you're using an equal power split, and we have this impedance being ZO, and this one being ZO root 2 or whatever, you know, it's that root 2 ratio. The ideal, some very clever chaps in past have already done all the research and homework on this, so I don't need to go through it, but the ideal angle here of that notch is 120 degrees. And there's a certain depth to it as well, a depth ratio, and that gives you a reflectionless connection at the frequency in the center band of our divider. So that's what that is. I'll leave it up to you to do more homework to find that information, or perhaps I'll throw that in another video, because this one's going on a little long. But so I have my 70.71 segments here, quarter wave transformers. I have a 50 ohm segment and then two 50 ohm segments on the output. And these are all implemented on the board as actual net tie components. So I'll do another video on how to make RF parts using net ties down the track. But you can see I've got that notch in the t-junction. I've got my ideal right angle corners on my quarter wave transmission line segments, which are actually components made in the copper. And then that's what I milled, and I measured it, and it works great. The Wilkinson divider is a little more tricky. So what we've done here is I've made a similar circuit, but the quarter wave transformers I've done as almost 180-degree arcs, with the calculations using arc length and all that to be a quarter wavelength long each. And those have a 0603 100 ohm RF resistor there for termination, for the differential termination for port isolation. And this is what it looks like in the actual PCB editor. Let me go out of single layer mode so you can see this is how the copper would look. And it's a little tricky on the output side of that, because I don't want to create too much coupling between the two transmission lines. They are microstrips, so they're mostly coupled to their reference ground plane underneath. But really, I wouldn't want to go with a resistor any smaller than an 0603 on this, because I don't want those coming too close together at that point and having any kind of differential coupling if I can avoid it at this location. So that's what it looks like. I haven't milled this one on the mill yet or measured it, but I'm going to do that, and perhaps follow up with that on another video down the track. So that's power dividers. Now, one last thing I want to leave you with as kind of homework is the question, can you have unequal power dividers? And the answer is yes. And you can control, essentially, let's just over here draw a power divider. Let's say I want more power coming out one side. So I'm going to, instead of having a 70.7 ohm quarter wave transformer, I might have a lower impedance than that. And more power is going to go out that arm, and I can have a proportionally smaller or higher impedance line on another side. So if you want to just take a small sample of a signal, you can actually adjust the power ratio going from one port to one port or another port. So we have port 2 will be a higher power, it's called P1, and port 3 will have a different power. That's P2. And so I'm not going to go through the math here because my math is horrible and I don't need to. There's a lot of wonderful calculators out there. And just really quickly, I'll show you one really great one. Let's bring up a browser panel real quick here. I'm just going to, actually, I have it open already. Let me bring this over here so you can see it. Let's go to calculators on microwaves101.com, which is nice. They've provided all these wonderful calculators here, and they're based on all the wisdom over the ages, so they're trustworthy. So if we have, let's see, unequal split power divider calculator, and there's different types of power dividers here. We don't have time to talk about branch lines and rat races, but we'll do that in the couplers episode, which is going to be episode 5, because I consider those couplers. But a Wilkinson power divider, and if I want a 3 dB split, this is going to calculate for me the quarter wave transformer impedances required to make a 3 dB split where port A is 3 dB higher than port B. So it has double the power coming out of port A than port 3. Port A than port B, I should say. And so this gives me all the different impedances I would need based on these textbook. These are the textbook formulas. All the algebra is already done for us. And if you wanted, you could take that information and put it in your own Excel spreadsheet, or as I will do, haven't done it yet, but I will be doing this soon, putting that into a script in Altium Designer. So it's all just there in the software ready for me to go. But that's how you do it. So I hope you've enjoyed this episode. Thanks for joining me for the OnTrack Whiteboard Video Series again on RF and Microwave PCB design. I'm Ben Jordan. If you like this, please give us a thumbs up. Please subscribe, share it with your friends. And if there's something you'd like me to cover in this series or anything else to do with electronics design, certainly leave comments and suggestions and do that below. We'll also provide some links below to other videos in this series, and stay tuned, and I'll see you next time.